For a couple thousand years, people misunderstood Newton's first law. I guess they didn't know it existed, really, but their understanding of motion was kind of flawed. They understood things like that they saw. If you rolled a ball along a floor, eventually it would stop. Friction would stop it. So people assumed that the natural state of things was for stuff to be stopped. However, Isaac Newton gives us this first law here of motion, and it's called nowadays inertia. And inertia says that objects tend to maintain their current state of motion. That means that if something is sitting still, it's going to sit still until a force acts on it, and it also means that if something is moving, it's going to keep moving until a force acts on it. Before Newton, there was this guy named Galileo who came up with an example that really explains this well. So I'm going to describe it to you. Galileo had this thought experiment. He didn't do this for real because he couldn't, but in his head he imagined that he had these ramps, and these ramps were frictionless. In other words, if you rolled something on this ramp, it would roll freely. There would be no loss of energy to heat or sound or air particles hitting it, anything like that. It would roll without any energy losses. So Galileo thought, well, if I put a marble or something right here and release it, if it doesn't lose any energy to anything, it's going to come back up to that same height, and it's going to go back and forth forever along this path. And then he took that to a different ramp, one that had a different shape, and he thought, well, if I have my marble here and I drop it again or let it roll, it's going to come back up to that original height again, and it's going to roll back and forth forever, except this one, it's going to roll a greater distance. So this distance over here is smaller than this distance. So then the real leap of understanding comes in this third one. Galileo said, well, if I release this one and I let it go, how far should it roll? If this ramp really doesn't, it just goes out flat, how far should it go? What do you think the answer is? Well, the answer is that it would go forever. And when you think about things out in space, like the Earth going around the sun and so forth, then you realize, oh yeah, that makes sense. The Earth is going to keep going around the sun for a long time, unless a force someday acts on it. Okay, so there's an introduction to Newton's first law, inertia. Newton's second law, better known as an equation, it says that a force will provide a mass with an acceleration. So you'll hear F equals ma. Force equals mass times acceleration. Force is measured in a unit called the Newton. Mass is kilograms, and acceleration is meters per second, or meters per second squared. I think I usually prefer to write it meters per second. So when you multiply these two things together, you get the Newton. So the Newton is the kilogram meter per second. Now, just as an explanation of this second law, let me show you this picture and this picture. Let's say these two guys both have the same strength. They both can apply the same force. So if they both have a force of F, well, the bicycle has a little mass and the motorcycle has a larger mass. So what kind of acceleration should we get if these guys both have the same force? Well, the bicycle, you should be able to accelerate more, and the motorcycle, you should be able to accelerate less. I hope that makes sense. Okay, so that's a really quick introduction to Newton's second law. Newton's third law, people are very good at saying this. They're very good at saying every action has an equal and opposite reaction. So like this guy is kicking off with his feet, he's pushing that way, and then the raft pushes him that way. So those two forces are going to be equal and opposite. The key idea here, or one key idea here, is that forces come in pairs. You're never going to have just one force without another force. There's always two forces. So you might ask, well, then what's going to move more? I mean, if the ramp has a very large mass, or the ramp, why do I keep saying ramp? If the raft has a very large mass compared to the person, then we would apply second law to it. We would say, all right, since the raft is so much more massive, then it's going to accelerate a little, and when the guy jumps off, he's going to get accelerated more. Or if maybe we could say that they have the same mass. If they had the same mass, then they would both go, at the same speeds in opposite directions. One more thing before I go, I wanted to explain something that I misunderstood for a long time, and I hope I can explain it adequately now. My problem was that if I saw this picture, I would say, well, okay, if the horse is going to pull the cart that way, and every action has an equal and opposite reaction, then the cart pulls that way, then this thing is not going to move. But obviously that's not true, because horses do pull carts, so there is motion. So what I was forgetting was what was really going on here. Think about what the horse is up to. The horse pushes with his legs that way, and that means the earth pushes back on the horse that way. So now when we're taking a look at what really matters here, if we're taking a look at this force, that force is the one that causes the horse and the cart, since they're connected together through this device, whatever this is called, that is enough of a force to accelerate the horse and the cart together. And there are other forces involved. There's friction with the ground and stuff, but make sure that when you're trying to apply Newton's third law, you're trying to take the big picture into account.